place winners. But we probably won't have the money on Thursday. We'll see. Maybe. I guess we've got a week and a couple days, so we might be able to get it done that fast. Usually it takes a little longer. Okay, so one of the things I want to do today, let me just talk about some end of course stuff, and then we'll talk about peripherals. And I'll probably let you go a little early, because how many of you went to the Micro 2 cup card competition and saw the tilt tables? So if you didn't, you missed it. It was kind of fun. Last year, the cars were better, but the tilt tables weren't as good. This year, the tilt tables were better, but the cars weren't quite as good. But we did have we had some good cars, and we had one car that made the whole loop in 22 seconds. I will say last year, the track was half the length of the one this year. So it was more challenging this year. We had quite a long track this year. And we'll probably do the same thing next year. Hopefully, I will have, one of the issues is we just continue to have a lot of connection problems, because there are a lot of connections that are required for the tilt tables. I did make a printed circuit board to try and simplify that. Unfortunately, there were a lot of I don't know, a number of students soldering the printed circuit boards blew traces off and did stuff like that. Truly amazing. So it was because we didn't have a lot of, there weren't very many markings on it to help them get things with the right polarity, and they put in stuff backwards and wrong. And anyway, so we'll work on that, but hopefully we'll make a few changes and then get some done. So, all right. So end of course stuff. So we'll talk a little bit about the peripherals today. So let me just tell you a little bit about the final. On the final will be a two-part final. There'll be a general part where I'll cover sort of basic things that we've covered in the course on the PIC and the KL25Z, mostly the PIC. And we'll talk about integrated development environments. We'll talk about assembler for the PIC, not for the KL25Z per se. If I ask anything about assembler in the KL25Z, it will be, how many bits of the instructions and about how many instructions are there. So those are a couple of things to keep in mind. Let's see. So we'll do that, and that'll probably be a front and back page. It won't be. It'll be pretty straightforward. I don't think you'll find that super challenging. And then the second thing we'll do is everybody will have to make a selection, and I'll probably have you give me that information on Thursday this week. So Thursday, I'll probably send out an email and just the next few times, Thursday and Tuesday and Thursday. So we only have 3 more classes after today. I'll probably I'd like everybody to attend those 3 classes, because it's so helpful to be on the same page. And I'll kind of explain that. So anyway, I'll send out an email to that effect. So one of the things that's part of the course is we said at the very beginning, and it's in the syllabus, that you have to complete all 10 PIC labs and the 2 KL25Z labs, and you can miss at most 1 total lab out of the 12 labs. So I have a list of people who are missing labs, more than 1 lab. And there are a lot of people missing more than 1 lab. So I'll go through that. Let me just project it, in fact. So basically, there are probably some people that have dropped the course or aren't participating anymore. But so Aaron, Aldo, Alexis, Amir, Ariel, Arthur, Brian, Chris, Danielle, Devin, Dylan, Evan, and so forth. So 3 labs, 7 labs, 3 labs, 2, 2, 2, 2, 2, 11, 2, 8, 5, 2, 11, 6, 2, 2, 3, 2, 7, 2, 2, 2, 2, 10, and so forth. So if you're on this list, this is the current official list from Anshul. And so that's what her records show. So even if you talked to her and she said you were okay, well, this is the bottom line. This is her current opinion on your status. So a bunch of people are missing 2 of the KL25Z labs. This Friday is really the last shot. Now I know for whatever reason the CodeWire wasn't installed on the first lab day, so you really just had last week to do them. And so this Friday will be the next time. I'd really like not to have people doing labs on Friday the 3rd of May. I think it is the 3rd of May is a Friday.
Yes.
Right, 3rd of May. So we'd like to avoid that. So if you have to do labs on that day, it may make you pay $5 to Anshul or something. But in any event, I won't do that really. But I do want you to just be aware. I mean, everybody's finishing school, and actually Anshul defended her thesis, so she's all done actually. But in any event, it's really good to get this done this Friday. So plan on coming in Friday and getting. You have all day to do it. Get what you need to get done. So if you're missing 2 KL labs, get them done. If you're missing a PIC lab, get it done. There aren't too many PIC labs. The people that have like 7, I don't know. Is Aldo here? No? All right, not surprising. How about Justice? No? I assume Joseph. I think Joseph probably dropped. So if you miss more than 1 lab, you will get an incomplete in the course. You will not be able to make it up until the fall. So that's fine. I will let you make it up. You don't have to register for the course again and pay another tuition, but you will have to get it done. And you have a year to get it done. And if you don't get it done within a year, then your incomplete turns into an F. So I will give incompletes to everybody who's missing more than 1 lab. If you're missing 1 lab, it's going to cost you 10% of your lab grade, which you probably don't want to do either. So you should get all your labs done. Just because you can miss 1 lab doesn't mean it's a good idea. And because really, my view is your project and the labs are really the essence of the course. So I assume most people would take that same view. So especially if you've got a couple of these labs, if you have friends that are like missing 9 labs or 4 labs or whatever, you can tell them, I will give them an incomplete in the course, and they should come take the final, and they can still make these things up, and they don't have to. Since this is a required course for most people's, how many of you is this a required course? I think it is for everybody, right? Yeah. So since you kind of have to take it, even people who've missed a bunch of labs don't really have to pay a tuition again. You can make up what you've missed and get a grade in the course. So it's really sad when people just drop off and don't kind of finish it, and then wind up getting an F essentially, and then wind up having to register for the course again and take it over, and you only get 2 shots to take required courses, so that's a little bit of a problem. So encourage your friends that may be slacking here to get off their butts, come take the final, talk to me, and I'll give them an incomplete if they think they can take time in the fall, or even they have until this time next spring. You just have to do it before the last class. You can't do it during the final exam period. So so a year from now, the last class, that's when they drop the F. So up until then, you can make it up. Okay. So anyway, a heads up. I'll probably forward this email or copy this and paste this into an email, and I'll send it out to everybody. I guess that's okay. I don't know. But what you should do this Friday when you're in lab, check with Anshul or check with Ryan and have them review the sheet and make sure, yes, you absolutely positively are good. Because what I don't want to do, what it's not going to work is a week from this Friday, oh, I need to make up 2 labs. Nope, not going to happen. In fact, really, I'd like it not to happen after Friday. If there's some really good excuse, like you were, in the hospital recovering from gunshot wounds, then we'll let you make it up next week. Okay. And we better see the bullet holes. All right. Okay. Any questions about the requirement to do all the labs, or at least miss no more than 1? Is anybody confused about that? Yes.
Do all the computers have the ID code word on them? Or is it just that one row?
Okay, that's a good point. I need to go talk to Lewis. I know Lewis probably hates me, but I'm developing a little bit of a love-hate relationship with them too. So I have communicated with them, and why this happens, I don't know. And then the fact that the computers get screwed up, that's not really their fault. Sometimes there are mechanical problems. I don't know. There are glitches in the system, Lord knows. And it's not their fault that that's how we manage these College of Engineering computers. That's how they get done. And Lewis is really a College of Engineering asset. He doesn't work for our department, he works for the College of Engineering. So I try and keep on their good side without, I don't go run into the dean and screaming and yelling. But it's really disappointing that we go through this when it's just the same code. I'm not asking for anything really special. So I don't know why that happened. I thought to myself the Thursday before that first Friday when the code wasn't on the machines that I should go to the lab and check it. But I thought, oh no, it's got to be there, because when he came and put MPLab X on, when it was missing the first week of the semester, I mentioned at that time that we would need CodeWire at the end. But, and also in previous emails I've stated what we need. Anyway, so without throwing any more stones at Lewis, I don't know, I have to go talk to him and make sure they've gone over and checked those computers. I did write them down, but then I haven't, so Thursday and then today has been major, I've been completely tied up getting that stuff done. In addition to that, the EPIC stuff I'm doing, we're presenting the final design review at the museum, at the museum this Friday, and then I'm actually teaching 5 courses this semester, so it's been a really busy semester. One course which we never intended to teach, and just we accidentally got people registered for it. And I probably should have screamed and yelled and refused to teach it, but I'm not that kind of person. So anyway, so it's just been a really busy semester. But after today, life is better, and so next week I'll really be working all the details, that some of which have been slipping a little bit. So I'll make sure that all the computers in the lab are good. I know most of them do have it, but there were 3 that didn't have it, I know. And I got those numbers and I'll give them to Lewis. Okay, any other questions about that? Good question. Yes?
Does missing one lab negatively affect?
Yeah, it's going to cost you about probably 10% of your lab grade. So you don't want to do that. Yeah?
Then can you get a list also with ones missing just one lab, if that's only 2?
Yeah, I don't have that information. Anshul's got that. So that's a great point. It's probably the entire class roster. Rather than, so it's what's best if you communicate personally with her in lab when she has the lab sheet. And then she can look at it and say, because that's the master sheet, and she's got it, she and Ryan control that. I haven't even seen it. So I could ask her to send me that, but then you have to type all that in, and it's probably the whole thing, and it's, so it's probably better just to ask her in lab. And then there were already a couple people that looked at this and said they didn't, that they talked to Anshul and this wasn't their understanding. So I don't know. Anyway, it's better to talk to Anshul in person. So even if you think you're all done, go to the lab, talk to Anshul this Friday. Yes?
There's not an actual lab this Friday, right? It's just makeup?
So theoretically, if we had been able to get the KO25Z lab done on time, the first lab, then this would be, then last week would have been the second KO25Z lab, and this week would be makeup labs and nothing else. But, a lot of people didn't get lab 1. And then admittedly, lab 2, the KO25Z chip, that Freedom board, the whole thing, and the IDE, there's some bugs in it. And the accelerometer lab, using the I2C, it's one of the most difficult modules to get programmed correctly on this chip. And so most of the time, I have standard code I run. I can run it 5 times in a row. 4 times it works perfectly, and 1 time it won't work. And it's absolutely, it drives me insane. But I don't really know how to fix it. It should work, it just doesn't always work. So I know there's sometimes problems getting this lab done, but you have to follow it meticulously, and also make sure that you hit because you're using Processor Expert, you do have to hit the Generate Code button. And I think that's in the documentation, but even if it isn't, when you get everything all set up, before you actually compile and run it, make sure you hit Generate Processor Expert Code. And if you can't, and sometimes that button's hard to find too, but it is there, and you should be able to do that. And sometimes that step's critical, or it is critical actually. Okay, so anyway, so try and get that done. if you have put in a significant amount of effort and you still can't get the program to run, then you know, I'll instruct Anshul to sign you off anyway. That's fine. But I would like you to give it a good effort, because it's kind of a fun lab to do. It, you know, it shows the effect of the accelerometer. All right. Any other questions? All good questions. Yes? No? Maybe? Okay. On Thursday, I'm going to have you tell me so in addition to back to the final exam. So there'll be a general part that'll be written, it'll be 2 pages, and then there'll be a 1-page, 10-question part and maybe 11 questions or even 12, that specifically addresses one of the modules you use in your project. And I have a set of questions for every module that anybody's ever used, and I don't think anybody in this class used modules that we've never used before. So oh well, maybe the OLED. So yeah, the OLED is one that hasn't been used before, so that'll be a leader. But other than the OLED, I think that's the only new module, and I'll write a module for the OLED. You can pick any of the modules that you use in your project. So if you use GPIO ports, you can do the GPIO module. If you use touch, you can do the touch module. If you used A to D, you can do the A to D module. If you used a timer, you can do the timer module. If you used the 2-line by 16 LCD, you can do that. You can do that. You can do any module that you use. And like I said, I think I have one for almost everything except the OLED. We haven't used that one before. And I'll make one for that. So that's an option too. PWM, H-bridge, servos, you name it. You can do one for any of those. And on Thursday, I want you to tell me what module you want to do for the second part of the final. And again, it's just 10 questions. Most people finish the final in about 20 minutes. It's not really too bad. If you actually wrote code for the module you're going to test on, you should do fine. If you had 2 other partners and they did all the work and you just watched, you might have a little trouble with it, so you might have to review. But if you actually wrote the code, you should probably be fine. All right, and I will review those. I'll go through a review on those things this Thursday, and next Tuesday I'll do a review for the final, including all the modules and the general questions. And I think there are some examples, not of the individual modules, but of the general questions on Blackboard, and if not, I'll make sure there are some. I'll look at that. Okay, so we'll go over, we'll basically go over that. Yeah, so basically we'll do the awards on the 2nd, and then we'll review for final on the 30th, and then on the 25th, we'll also do review for the final, and I'll also take your module questions up. I'll probably update the syllabus to show this. And again, this is really, Friday hopefully is the last day to make up KL25C labs, and I'll also let you make up PIC labs, even though we're already past that day. That day was theoretically there, but we'll go ahead and do that. Okay, good. All right, any questions about the schedule for the rest of the year, the final exam, and getting the labs done? We're all good? All right. Okay, so I'll just kind of go over, I think I'll go over general peripherals here just a little bit, and then I'll talk a little bit about the kinds of questions I might ask. And most of these will be PIC peripherals. I may talk about the KL25Z a little bit as well. Okay. So let me just say one other thing, and that is that I was in general pleased with the work you did and presented on last Thursday. I thought it was good. Got pretty good exposure. Could have been a little more. Could have been a few more people, but because the class meets late in the day, people were kind of fading out. But anyway, I thought what you all did was great, and really almost everybody put in a reasonable effort, and I was pleased with that. I know some people worked really hard. Some people struggled more than others. Some people bit off bigger projects. Some people bit off more than they could chew, but still recovered and did okay. And that's fine. I do, it's always good to get a little feedback. One of the things the reason I do projects and the reason we do labs is because I feel like that's how you learn. You can sit here and have me lecture, till I'm blue in the face and you're sound asleep about embedded design and microprocessors, but until you actually write code and interface things, you really don't know anything, because until you actually get your hands dirty with the hardware and with the software, it's really theory that doesn't mean a whole lot. And I hope you came to appreciate that, and hopefully if you graduate and you have a job where you're actually developing microprocessor applications, embedded designs, that sort of thing, hopefully you now have at least an idea of how to start, how to approach these problems, what an IDE looks like. Maybe, hopefully you played with the debugger a little bit. Hopefully you have some sense about what you can and can't do, and about what kind of level of effort it's going to take to implement certain things. Some things would seem easy or hard, some things would seem hard or easy. A lot of it depends on how difficult it is to write the software. Hopefully you gain some appreciation with the human user interface. Those turn out to be very difficult problems. It's hard to write a robust interface that anybody can walk up with very little information and figure out and use effectively without getting frustrated and irritated by your interface. And hopefully you learn some things about that. Okay, any general comments about the projects, about your experience on last Thursday? Any thoughts on that? Everybody's good. Let me ask, I'm just curious, how many of you felt like that was something that caused you to learn a lot, or how many thought you learned a lot? I'm curious. How many felt like it was a waste of time and we should never do this again? All right, that's good. I don't do it just for the hell of it. I do it because that's what students tell me, that it really was meaningful to them most of the time. All right, great. Okay, so there's a whole bunch, so hopefully by now, and by the way, I had a whole bunch of sensors that nobody used. I had a gas sensor, I had an alcohol sensor, I had I don't know, the list goes on and on. There's a whole bunch of stuff that people could have chosen to do and nobody asked about, which we actually mentioned way back when, but nobody got excited about it. But anyway, so hopefully you realize when you are working for some company and they say, okay, Joe or Joan, you should go build, we want to build this device. Go for it. And, so you're going to, it's going to be challenging. In some cases, it may be a very novel thing, like using ultrasound, shooting ultrasound through blood and trying to get some new measurement about what's in the blood. That's pretty cool, but that's more basic research. And typically, you're going to see people with advanced degrees biting that stuff off. But just the bread and butter stuff of, taking things that are relatively straightforward, hooking them up, and making a product, that's happening all the time. And there's a tremendously large number of projects that are totally doable by existing technology that would be very useful to people that just haven't been done yet. Or there are ones that are out there, but they're not very good, and you could definitely improve them. So you may find yourself in that situation, and of course, hopefully by now you figured out there's a litany of things you can use. There are just so many amazing modules and chips available to be interfaced, almost whatever you need. And so the tools we have at our disposal are great, and it's just a lack of time and energy to get it done. And you may very well find yourself doing some of these things. So we'll just go through a few of them. So just general purpose input-output pins in and of themselves are tremendously powerful. One of my friends worked for one of the soda dispenser companies, and they patented a use of GPIO pins where they use them to monitor the ice buildup on the cooling coils in the tank where they flow the drink through it before they dispense it out the nozzle. And the way they do that is very simple. They have 2 pins. They send a signal out on one, and then with the other pin, they have it set as an input, only an input to their A to D converter, and they look at the A to D voltage value. And the nice thing is they only have to send energy out every now and then. They maybe for a few milliseconds, every 10, 20 seconds, maybe every minute, so that the duty cycle is maybe 0.001%. 99.999% of the time, there's no power to these pins, and that prevents them from developing, some sort of electroplating from minerals in the water and corroding and doing weird things. And if you really are super worried about it, you can frickin' reverse them. You don't even have to use. You can take the one that's the GPIO pin and the one that's the A to D, and you can switch their functionality if you want in your software and make the one that was A to D now GPIO and the other one the A to D, so that you can really minimize the the amount of corrosion and stuff that occurs if you just left them powered all the time. They could maybe cause electrolysis, could plate out something on them. But if you leave them turned off most of the time and you only turn them on when you need to make a measurement for maybe a few milliseconds and then you're done, you can get these things to do all sorts of cool things. And what happens is when the ice grows to the point where it encompasses the GPIO line, the A to D line then senses a major change in the voltage that it's measuring relative to to the microprocessor or ground, and so it can tell when that ice has covered that GPIO pin. And so with just stupid little GPIO pins, you have an ice sensor or a fluid level, assuming it's not sterile, deionized, distilled water. It should conduct, and you should be able to pick something up. You might not want to use that particular approach for gasoline, just in the chance that there might be a spark, but there are other things you can do for that, obviously. You can, so just GPIO pins can be incredibly powerful, used for all sorts of things. And then we have all these serial protocols that you have all sorts of access to. We didn't do anything specifically with USB, but because it's kind of an advanced, it's kind of a notch up. You have to read a fair amount before you can really weigh in. There's software you have to do. There's a 5-volt voltage controller you have to support, things like this if you're going to do the master side. But it's not all that difficult, and it's something you can definitely wade into. But you can see how super powerful that is, and if you only want to transmit one wire, if you only want to receive, you just need one wire plus a ground, and it's readily available in very inexpensive add-on modules. And then of course built-in SPI, built-in I2C. Well, the UART's built in too, but you have to typically get a UART to USB converter. And then again, the A to D module. Hopefully you've learned a few things about that, some of the kind of do's and don'ts and the limitations. The A to D module on this low-level PIC is not super fast. You can probably get readings at a couple of kilohertz, but that's about it. And you only get 10 bits, so there are some limitations. But on the KO25Z chip, it can do them a little significantly faster, and it is 16 bits. So that's, and then the D-to-A, we didn't do an experiment with the D-to-A, but it's definitely a nice way to establish a voltage level. You have to remember though, you must buffer the output because it's done with a resistor ladder, so you can't source much current or sink much current because it would screw up the resistor ladder. Then you would have more voltage drops across the parts conducting than you would across the parts not conducting, and it would screw up the division. But all you have to do is put an operational amplifier on the output, and boom, now you have it nicely buffered with a very, very high impedance input and that draws almost zero current, and a nice low impedance output that can power other things, and you can even buffer that if you needed to. So the D-to-A can be very useful. This is, of course, when we process audio these days, whether it's from a microphone or from an MP3 player or whatever, we're going to go through the A to D and then the D to A. And obviously you can filter that in digital mode if you want as well. You can do a fast Fourier transform and notch out certain frequencies and all sorts of crazy things. Needs a little more processor speed than the entry-level PIC though. We have a capture, compare, and PWM modules, and all of you should have done the PWM lab where you can see how you can control brightness of nonlinear things like LEDs, how you control the speed of nonlinear things like motors, and how you can control servos. And there are a whole number of PWM things you can do. Associated with timer 1 to control its timing with hardware. That's really nice. Some of you that did the ping sensor did that, some of you didn't. And then you all did touch sensing labs, so you saw how to use that. The touch sensing module on this chip is a legacy module. For the up-to-date chips, they use assembly language routines that are in a library that you can use, and they use the A to D converter instead of a touch sensing module. They work in a similar way, but it's a little more robust than the module. They really had a lot of problems with these modules because of the Achilles tendon that noise at certain frequencies would just kill them, and there wasn't any way to work around it. Anyway, and then you learned about parallel and serial LCD drivers, or I2C and parallel. And then we didn't use watchdog timers. We didn't use sleep mode. Those are some things that we could have explored a little more. And then we didn't really mess around changing the system clock a whole lot, but that's another area where you can do all sorts of things. Okay, so you should know, when it comes to GPIO, you should definitely know that all the pins on the chip can be GPIO pins, but some of them are tied up for other activities. So I was a little surprised. There were a number of people that just, without even thinking about it, were going to use port A pin 0 and port A pin 1 and port A pin 3. Well, pin 3 can only be an input, but normally if you want to have debug capability, then you really have to keep port A pin 0, port A pin 1, and port A pin 3. You kind of have to do hands-off on those. They're also used for flashing the chip when you use the PICKIT header. Now there are other ways of programming the chip without using those. One of the things you can do is you can program the chip and then put jumpers on and connect those pins for some function once the chip's programmed, and they can do you can use them just like you would. The other thing you can do when you need to do in-circuit debugging, when you would start a new project and once you picked out the chip, then the next question was, do you have a debug header? And you always answer that no. But it turns out there are debug headers. And so I thought I'd mention that because we didn't really talk about that. But a debug header, so our chip has 20 pins, right? And what the debug header does, it has like 24 pins. And it kind of comes in a special socket. So you have a special socket that has 20 pins that plugs into this. So normally you'd unplug this chip and you plug this in. It's a little harder with surface mount, but you can still, there's ways of doing that too. And then it has a couple more pins here, and into this slot, you actually plug this special copy of it's essentially a chip to mimic the 16F1829, but it brings out the master clear pin and port A0 and 1, the debug function, separately from the actual pins. So here's port A0, here's port A1, here's port A3. It puts those in this normal footprint, and it lets them function without having to use the debug capabilities. And then it lets you hook this up to your debug header, and so you actually bring out the debug function separately than the pin. And so now you can actually have your device using port A0, 1, and 3. 3 is only an input though, but these can be inputs or outputs. You can use all those pins and debug it at the same time, but to do that you have to have this special header chip plugged in to your board instead of your standard chip. And so there are ways of testing it with the help of a special debug header if you want to use those pins, but you also want to have debug capability while those pins are functioning. And you can actually do that with this special header. I have one. I've never gotten it to work. It's a little bit tricky. I haven't spent a lot of time trying to do it. Okay, you should know, yeah, go ahead.
When you're using that debug, does it use different pins on the pick?
Yeah, it's a special chip
Okay.
that brings out those 3 pins completely separately. So it has 3 new pins, they have 4 because it's even.
You can use all 20 GPIO pins.
Well, you still have to use power and ground,
Yeah.
but 18,
So all
you can have 18 GPIOs working and debugging them. Yeah, that's what it lets you do. Remember, every GPIO pin, all the ports have 3 associated registers, right? Well, actually more than that. They all have actually 6 on this chip. They all have a tris, a port, a latch, and they have an AND cell, and then a weak pull-up, and a input level control. So you should be familiar with these 6 registers, and you should have some idea how they function. Now the weak pull-ups are so weak, they're kind of not useful in my view. I tried to use the weak pull-ups in place of the 10K resistor on the RB3 input, the push button that we use in our labs, and it just doesn't work. You need a little stronger pull-up resistor. So they are pretty weak, and this is the only real advantage of this is that for a real commercial product, they recommend that you don't have floating pins, and so. But normally you don't want to program pins as outputs unless because you don't want the voltages appearing on those pins. So normally we'll program them as inputs and go ahead and turn the weak pull-ups on pins you're not going to use. And that way you don't have to put external pull-downs or pull-ups on them so that you don't have floating pins. Because floating pins could theoretically cause problems with the internal hardware. It's not a good idea to have them. You can induce electrostatically currents on them. So you kind of want them pulled up or pulled down, and you can use the internal pull-ups to subserve that function and keep you from having to put external resistors on. That's about, in my view, the only thing they're really good for. If you really need to pull a pin up, they're not strong enough to really do the job for that. Remember that the AND cells must be set for analog function. They must be cleared for input, and you should also clear them if you're going to use it for GPIO output. So it's a really good idea to clear these bits if you're going to use them for GPIO or any of the other modules, except for one of the analog functions. What are the analog functions on this chip? Somebody tell me, what are the classic analog functions on this chip?
A to D.
A to D?
D to A.
D to A?
You do, yeah.
No, that's digital. With proper filtering, you can make it like a D to A, but it's considered digital out. It's either 1 or 0.
Touch sensing.
Huh?
Touch sensing.
Yeah, touch sensing. With the touch sensing module, it is absolutely an analog function. And all the touch sensing inputs are analog functions, but they use with the new approach that they've used, they use D to A converters, and typically they're putting they call them DACC, digital to analog conversion computational. So all the new modules, even in this family, the new chips all have these DCC modules, and the DCC will average some number of samples, and it's particularly suitable for the touch sensing function. Again, though, you have to download this library assembly language code, and you're not allowed to change anything on it. You just have to use it as is in order to get the D-Day to work properly and to be robust, which is, and this robust use is really nice because it allows for proximity detection, it allows for different pressures of sensing, it allows for all, sliders and all sorts of stuff. So it allows for gestures where you don't actually have to touch the buttons. Well, you don't really have to touch the buttons ever, but where you can hold your hand sort of above the sensing area, and you can do swipes and things like that, and it'll sense those gestures. And there's a gesture library that they have available. And you're missing one. What's the other one? That's the other analog function. Well, there's a fixed voltage reference. I'm not really counting that. That's also one. What? The comparator. It has a high-speed comparator. And that's very nice for you can use that in a number of different ways. Now, some chips in the same family have programmable logic on input pins, and some of the chips have just a number of additional features that we don't have, like the computational A to D converters and operational amplifiers available on the inputs. So there's all sorts of stuff available that we don't have on this chip that is included in this family. Okay, so you should know a little bit about this diagram, especially if you're going to take the GPIO test. So you really need to understand this. And not so much because you need to memorize this low-level PIC, but because this is typical for almost every GPIO pin. It has this functionality, more or less like this. It's got a flip-flop associated with the output. It's got a tri-state buffer that connects the output of the flip-flop to the pin, or not. Okay, it can tri-state it or it can connect it. And typically, there's instructions that read what you've written to this buffer here, to this flip-flop, and other instructions that actually read what's on the pin. And then you have the analog function that basically blocks the digital function, and then you have the fact that in some cases we have a port read which lets us read the pin. We gate the pin onto the bus, and a latch read where we get to read what's latched into the output flip-flop, regardless of whether it's connecting to the pin with the buffer or not. So you should be familiar with this. It's a good, and you should know about the protection diodes and kind of, how they keep static from killing our CMOS. Yeah, you should know that we can source or sync 25 milliamps, but generally we prefer to sync it than we do source it, because if we source it, we have a smaller budget on our, all the current we source has to come into the VDD pin, and our budget from VDD is smaller than if we sync current, it goes out the ground pin, and the ground pin has a bigger budget. So we would prefer to sync most of the time than we would to source. You should know that many of the pins have interrupt capability. With the interrupt on change part, there's one pin that has the legacy interrupt pin, but all the rest of the pins are interrupt on change pins using peripheral registers and things like that. And you should know the maximum and minimum voltages, and you should know that your input level setting determines what the chip recognizes as a high or low. You should know you have to kind of calculate that depending on what you're running, what voltage you're running the chip at. Just be aware of that. I don't care that you memorize those formulas, but you should know that you can actually calculate the specific voltage level where the datasheet guarantees the microprocessor will recognize that as a 1 versus where it'll guarantee it'll recognize that as a 0. And then in between those two, you're not really sure how it's going to recognize that voltage. You should know if you run the chip at the lowest voltage you can run it at, that you can't run it at the highest speed. You have to be above, I think, maybe, I forget, but you've got to be above the 1.8 volts to run it at full speed. Maybe you have to get above 3, I forget. You should know when you want to drive, well, one thing you should know for sure, I don't know if I put this on there or not, but when you do GPIOs, I always ask this question. And by now this should be falling off a log, but I know there'll be people that'll miss it, and it drives me crazy, so don't do that, okay? So here's the pin, and you want to make this an input. So you clear the AND cell bit, and you set the tris bit to a 1, and everything's ready to go, okay? So you're going to put a pull-up, an external pull-up to VCC, and then you're going to run this out, and you're going to have say a push button switch here, and this is going to go to ground. All right, when you push that switch, you ground this and you read a 0. When the switch isn't pushed, it's pulled up and you read a 1. So if I give this to you and I say, here's the pin, here's a pull-up resistor, and here's a ground connection. If I wanted to read 0 on push, how should I wire it up? You ought to know that this has to be pulled up with the resistor, and then the push button, this has to go to ground, right? You should, then if I ask for it the opposite way, let's say I wanted to read a 1 and read a 1 on push. So then in that case, I want this to go to ground, and I want this to go to VCC, okay, or VDD, whatever, right? You should know this pull-up resistor has to go on this side. It has to go on the pin when it's not connected so it doesn't float. If I take this off, I have no idea what this is going to read. As I bring my hand with an electrostatic charge on it close, I'll induce a little voltage and it might read a 1. Or maybe my hand's got a negative voltage and I'll induce a lower voltage and it'll read 0. You have no freaking idea what it's going to do. It's not something you should ever do. So you should know this. So make sure if you do the GPIO module, you know how to wire up a switch to a microprocessor input pin. And that you have to either pull up or pull down, and then the switch shorts it the opposite way, right? And typically, what do we use for those values? 10K, that's kind of the classic. You know, we use 10,000 ohms, somewhere in that ballpark. All right? All right. If you're going to use a transistor for a switch, remember, if you're going to switch the high side, which is what we normally want to do, you use a PNP. If you're going to switch the low side, we use an NPN. And we do the same thing with a FET. We use an N-channel FET for the low side, a P-channel FET for the high side, but we'd rather use an N-channel FET on the high side too, and so now we have to do charge pumping and everything to actually switch it. Okay, so I probably want to ask you about FETs, but I may ask you about BJTs. You should know how to use a BJT to drive a little stronger load. Now, let me ask you this. Let's say we're working with this. We're switching the high side, okay? So switching the high side. So here's VCC, and then we come down here, and we go into our BJT. So that's the emitter, that's the collector. Here's the base. We usually have a resistor control the current through the base, and then here's our load, and here's ground. Okay, so this is an NPN. That's typically what you want to put there, and you should know to turn this off. You take this high. To turn it on, you take it low. Okay, and so this can be driven very nicely. If this VCC could be 9 volts, that's fine. This can be still driven with a 3.3 volt microprocessor operating at 3.3 volts. It'll work fine. You do need to do a little calculation to make sure that you're you do need to do a little calculation to make sure that you've got sufficient base current flowing to drive it fully into saturation when you turn it on. And that's how you size this resistor. But usually it just takes a few milliamps to drive it into saturation. But you should do the math. In this case, you know, 9 volts, this resistor going to ground, what is that going to take? And figuring a 0.7 voltage drop across the junction, you should be able to figure that out. Okay, I might not ask that on the test, but you should know that in your head, and that'll allow you to size this resistor appropriately. You don't want it any smaller than it needs to be to get that sufficient base current to drive it fully into saturation, so it's all the way on. Okay, any questions about that? Okay, and yeah, okay, and you know, if you have a bunch of things that pin needs to drive, normally you can't hook up a bunch of stuff. Remember, you know, you've got a 25 milliamp limit on how much that pin can sink or source, so you can't just stack on, you know, 4 or 5 LEDs. It won't work. It'll burn out the board. So, and these are really nice. They're cheap. They're small. The ones on your board, I mean, you can see how small they are when you get them in surface mount. You've got you've got a 2N3904 and a 2N3906 on your board in that 2 transistor switch. And it'll handle, I don't know that it'll really handle 200 milliamps, but it'll handle over 100 without any trouble. Okay, let's see, I think. Remember, for an LED, if you're going to drive an LED directly from a pin, that's fine, but you should keep in mind you need a current limiting resistor. You don't want to put more than about 20 milliamps through that LED, and maybe not even 20. Some of them are kind of bright. The power LEDs on our board are pretty bright. They're almost blinding. So it's almost better not to. I probably should have made those resistors bigger to make them a little dimmer. Remember, the super brights can take a lot of current. And remember that there's a pretty good voltage drop with blues and whites and some of the funny colors. But with red, green, yellow, it's about a 1 to 1.5 volt drop across the LED. And you have to subtract that from your source voltage, and then that will tell you how much voltage is dropped across your current limiting resistor, and that will tell you about how you need to size that resistor to get 20 milliamps. Okay, so again, this is the switch. I guess make sure you understand this. Well, so the pull-up has to be on the MCU side, right, or the pull-down. You don't ever want this pin just to be floating free. It's amazing. All right. Open collector. You should know when we want to do open collectors. This is how the I2C bus has a number of slaves and a master on the bus all at the same time, and there's no short circuits because they're all connected with open collectors. So the most they'll do is pull the bus to ground. And the only way the bus goes up is through a pull-up resistor. In this case, we don't usually use a 10K. We use something between 2.2, 2.4, and maybe 4.5, maybe at most 5. You want it low enough that it moves the bus up fast enough that it can support fairly good data rates. But as you drop more and more stuff on the bus, then you generally have to raise the value, or maybe lower the value of the resistor actually, because of the parasitic capacitance and stuff that's there. So sometimes you have to do some calculations to figure out the best value for the pull-up, but usually between 2 and 5, something like that. Okay, and again, you don't have to memorize these tables, but you should just be aware where to look in the data sheet. So if I were to give you this table on the test and ask you, you're running your chip at 4.5 volts, and I have a peripheral device that is sending a positive to your PIC that's 2.1 volts. Is that going to be recognized as a 1? And if your input level setting is selected for Schmidt trigger, you should be able to answer that question by looking at that. Okay. I wouldn't ask you to have that memorized, but I might ask you that like that. It's a great question. Okay. So the other nice thing about these GPIO pins, let's say you need a certain protocol, like you need the Samsung IR remote control protocol that your television set and your stereo and a bunch of your stuff probably works on. That IR protocol, there's no module for that. But you can totally use that protocol simply by implementing it in software and using GPIO pins to do it. You do have to have a IR LED or an IR photo transistor, actually. Okay, so I'll talk a little bit about UART, SPI, I2C. Okay, so let's talk about these briefly. So remember, on the UART side, we always have, it's not really a master-slave relationship. With the UART, we're generating the clock at both ends, and it's in asynchronous mode typically. There is a synchronous mode, but we normally don't use that. So in asynchronous mode, both ends, we generate the clock there at each end, and the clock isn't shared, and then we just send the data. But hopefully they're both using the same clock. Although your module on this PIC has the ability to auto-detect the baud rate of an incoming signal and set its baud rate appropriately. That you can do that in software, and it has that ability. When we talk about RS-232 or 422 or 485, these are transmission protocols that involve funky voltage levels on lines, and it's not really, the UART itself is TTL level. In other words, 0 to 5 volts, 0 to 3.3, whatever the processor's running at. The RS-232 in particular, is classically plus or minus 15 volts, plus or minus 9 volts will work, but it needs to be a pretty healthy plus minus voltage. And that's because it's a little less sensitive to noise when you do long runs, and some of these could do long runs. And I forget the 422 and stuff, 45. These were typically used to connect various instruments together. A lot of these protocols have kind of gone away, although you'll still find a lot of legacy stuff using them, but they're pretty much gone. But the UART is here to stay. It's very, very useful. Sometimes sometimes we call it SCI instead of UART. Anyway, we also have then the SPI protocol, where we do have one master, and we may have several slaves or just one slave. Usually the slaves take their own line in addition to the 4 lines in the SPI interface. So there's 4 lines typically. There's a MOSI, a MISO, a clock, and a slave select. And then if you need another slave, you have to add another slave select line for the new slave. There are ways of getting around that, but that's typically how it's done. And then the I2C, 2 wires, that's it. Plus obviously power and ground, but SPI needs power and ground too. So you could say it's a 6-wire protocol. So just 2 wires plus the power and ground. And you can have up to 127 different slaves on the same I2C bus in theory. In practicality, that would give you so much parasitic capacitance that it probably wouldn't work very well. So you probably can't do that. And also you might not have that many parts with unique enough addresses to actually do it. Because most of the parts have their address mostly set with 1, 2, or 3 bits you can change, but that's about it. You usually can't change the other bits at all. And then there's a CAN bus, that's typically used in automobiles. There's a 2-wire interface, there's a micro wire, a 1-wire, there's a whole bunch of other stuff. And normally we're going to bit bang these. The CAN, you're normally going to have a peripheral module to support that. We don't have that on this part, but the PIC 1829 LIN does have a CAN bus on it, is for automobile purposes. So here's the UART. Normally you have a start bit, 8 data bits, and then a couple of stop bits. And in the old days, the last bit would be used as a protocol bit. Nowadays it's used as data. We'd use odd parity or even parity maybe with that bit, but now we don't do that anymore really. And it's typically run in synchronous mode. It's typically run in asynchronous mode, where you can send and receive simultaneously and independently. So it's very nice. I'm not going to go through the block diagrams. So it is full duplex. That means data can go in both directions simultaneously. Typically, in this chip you've got a 2-character input buffer, so you can bring in 8 bits, and then you can be bringing in the next 8 bits without destroying the first 8 bits. But the 3rd byte that comes in, that overwrites one of the. I guess the first byte gets overwritten, and then you can have there's only one buffer for the output buffer. You load it, and then it's immediately shifted out. It's shifted to the shift register and shifted out. There is a 9-bit feature, which I don't think that's used very often. It's mostly used in 8 bits. And there is a 9-bit address detection, but typically we use 7-bit addresses. And then the 8th bit is our read-write bit. There is input buffer overrun and error detection, all sorts of fancy things. With UART we normally don't use addresses. This is kind of a special mode that I've never used it. That's pretty rare. And then there's you can get framing errors. And you can run in synchronous mode where only the master generates the clock, but that's kind of rare too. But there were some legacy chips that didn't want to implement clocks that use that. Mostly we don't talk to other chips with the UART. Normally we talk to We talk to more complicated devices, like we might talk to a GPS module. So the GPS module will send out its various sentences using UART, and then we have to decode those sentences and pick out the sentence we're interested in. All right, additional signals, clear to send, data carrier detected, blah, 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 blah. One end was always called data communication equipment, and the other end was data terminal equipment. Very confusing. It was always hard to figure out which way was which, and then we had things like null modems, and sometimes we crossed over and sometimes we didn't. It just got ridiculous. We don't really use any of this stuff, but this really was back in the days when these RS-232, when our UARTs were almost exclusively used over telephone lines. And that's obviously not the case anymore. And I'm not going, the DB9 connector, still available on most desktops if you want to plug them in, but most laptops don't have these at all anymore. It looks a little bit like a VGA plug, but a VGA plug has 3 rows and a lot more pins. It is not a VGA plug, it's just a 9-pin DB9 we call it. And this used to be the old, essentially the connection for RS-232 devices. All right, I'm not going to talk anymore about RS-232. You don't have to know anything about RS-232. And again, so I2C, there's 2 lines, a serial clock line, SCL, serial data line, SDA, and obviously a ground. You have to have a ground. But that's it. That's all you have to have for I2C. And you have typically 1 master, but you can have multiple masters. There's limited multiple master support on our chip. And then you can have a bunch of slaves, theoretically, each one with its own unique address, and you get 7 bits of address, so that's 127 slaves. You always drive these lines with open collectors, and you need pull-ups on them. You only need the pull-ups in one place, though. And sometimes you have to check. Sometimes your slave will have a pull-up on it. You may buy a module that has pull-ups built in. If that's the case, then you might want to deactivate those or cut those out, or maybe cut the ones out on your board. So you kind of have to pay attention to whether the modules you're hooking on to your I2C lines have their own pull-ups or not. You probably can get by with that, but if you get too many pull-ups, then it's gonna cause problems. And so anyway, I'm not going to talk about this much. There is supposed to be a 0 address. So there's 120 addresses, but the 0 address is supposed to refer to all slaves. All slaves are supposed to respond to the 0 address, but most slaves don't support it, so it's kind of bogus. And so, yeah, I'm not going to talk about this. I'm not going to test you on this. You should know, though, from your lab that there's sort of this litany of things you have to do. You send the start bit, you send the slave address, you add the appended reader-write bit, then you wait for the acknowledge bit, then you receive or send the 8 bits of data, and then you either get or send the acknowledge bit, depending on whether you were writing or reading. And then, if you're done, you send the stop bit. And if you're not, then you can send the restart bit and get another, or you can just get another. If you don't send the NAC, then you can wind up reading another 8 bits of data, and you can just keep going till you send the acknowledge bit. Okay. Anyway, typically about 100K to 400K is kind of the standard rates, but you can sometimes run it a lot faster than that. If you run it really fast, you need lower resistance pull-ups. Okay. So examples that we used with I2C, we ran the 2-line by 16 LCD display with I2C. We also did parallel with that, but we used I2C. And then the accelerometer lab we did on the KL25Z board uses I2C. So those are some examples. Again, 4 signals for SPI, MOSI, MISO, clock, and slave select. In this case, the slave does have to be able to tri-state its connections if there's more than one slave. So when the slave is deselected, it needs to tri-state its MOSI and MISO connections. Otherwise, these are driven. They're not open collectors. And so, since they're driven high and driven low, if you're going to have more than one slave, you have to deactivate. You have to tri-state the output, not so much the input, but you have to tri-state the output from the slave. That would be MISO, the master in, slave out. So the slave output has to tri-state if the slave's not selected, so you can have more than one slave driving the bus, but not at the same time. And if you have more than one slave, typically you're going to add an additional slave select line. So now for 2 slaves you'd have 5 lines. For 3 slaves you'd have 6 lines, and so forth. And remember, it always sends data both directions. In this case, where is the clock generated in SPI? Where is the clock generated in SPI?
Master.
The master generates the clock. Where is the clock generated in I²C? No, the master generates the clock, but the slave can do clock stretching by holding the clock line low. If it's being pushed too fast, it can stall and give itself time to respond. Where is the clock generated in UART? Both ends, unless you're in synchronous mode, but that's rare. So for sake of any test question, UART, we generate a clock both ends. SPI and I²C, only the master. Okay? All right, I'm probably going to stop here. We'll finish some of this up. Let me just say one more thing. So we are starting our ABET collection. We got a full 6 years, which is the maximum in 16. So we're not actually going to get inspected again until 16 plus 6, 22. But we're going to start the process because we use the ABET process to do course improvement. Although we do course improvement anyway, but we do it formally. And so anyway, one of the features is we like to collect student work. And so I will give you a 1% bonus point on the course if you put together a little folder with class notes, although I know everybody takes copious class notes. I see that. But maybe you can come up with something. Class notes, homework. I know everybody does their homework too, right? And then your lab sheets, and maybe kind of what you did in labs. You know, just put together a little course notebook. It doesn't have to be extensive. Just has to reflect, you know, show that you actually did some work in the class. And then maybe a description of your project, and maybe the code for your project. And then if you want to put in PowerPoint, you can do that, although that gets kind of bulky. You don't really have to. And put that in a little notebook. And if you put that and give it to me at the final exam, or anytime between now and the final exam, then I will give you a 1 percentage point bonus for the course. So I would like maybe 3 good students, and it'd be nice to have 3 less than, you know, outstanding students do that. You know, you don't have to be flunking the course, but if you're, you know, whatever. So if a few students would do that, that would really be helpful. All right, any questions? All right, you guys have a great evening.